I have chosen a topic nowadays. It has been a very hot topic, machine learning. How the machine learning can be used for automatic interpretation of subsurface geologic features from the data acquired on the surface. So this is the topic I have chosen, and I will show some of the examples how the machine learning can be used for delimitation of the subsurface geologic features from 3D seismic data. So the outline of my talk is why should we do seismic experiment, and then whenever we do the seismic experiment, the basic steps involved are how we'll acquire data, how we'll process and image the data, and then how we'll infer from the image, or we define as the interpretation. What sort of advancement has taken place in the seismic imaging and applications? What are the current challenge and how we can alleviate those challenge? And that challenge I will pose over here, and through artificial intelligence and machine learning, and I will show some of the field examples from the seismic data, and finally remarks and acknowledgement. It has been very crucial to understand some of the methodologies that can be used to extract reliable subsurface information from the data acquired on the surface. And that gives us a lot of information to take a decision whether we do exploration of hydrocarbons, whether we do or understand some of the earthquake processes, whether we understand some of the geotectonics and basin evolution, whether we identify mineralized prospect, groundwater contamination. And seismic has been one of the most geophysical tools that provide subsurface information in terms of physical properties like seismic velocities and structures like faults, seals, dikes, many other features. I will show some of the examples, and they contain useful information to derive some of the information from the surface field data. So three basic steps are involved: data acquisition, data processing, data interpretation. I am showing through this slide that when we acquire seismic data, we adopt two important approaches. One is the near vertical reflection profiling, where we shot at this point O and record the data that comes from different subsurface depths by reflection, refraction, diffraction, and then record at the surface by an instrument called seismometer. When we record the data at the near vertical range, that type of data is called near vertical reflection data. And I am showing some of the examples, just bottom panel here, near vertical. And another set of data we do when we explode at this point and record at the wide angle range, and we define at the wide angle reflection. This also gets the data from different subsurface horizons after getting reflected, refracted, diffracted, etc. So this is one of the schematic diagram in the offshore. This is one of the schematic diagram in the onshore. So one of the example of the wide angle data like this, mostly the wide angle data is single fold, but the near vertical data are multiple fold. And when we process the data of the near vertical data, near vertical reflection data, we get this type of image, subsurface image, that shows a lot of structural details. But when we have the wide angle data, single fold data, and we process that data and get the variation of the subsurface physical properties in terms of seismic velocities, and that shows. So why we do have these two type of experiment? Because this gives this very good structural information, that near vertical data, and the wide angle data gives very good velocity information. So if we have coincidence near vertical and wide angle data, that gives a holistic information both in terms of structures and physical properties. That's why two types of seismic data acquisition is there. Next step, But whenever we acquire data, we need to get the subsurface image. There are several advanced tools available, and that tools can be employed to the suitable data, and we can derive some sort of subsurface information. I am showing an example of the common reflection surface track image that shows how the subsurface image looks like. We can also do full waveform travel time tomography, and that shows that subsurface variation in the physical properties, as well as two-dimensional full waveform tomography that shows very finite details of the subsurface structure, and this shows some sort of imaging, all the finite details, faults, etc. And then we can have some sort of seismic attributes computation, and that attribute computation help for characterization subsurface reservoirs. The reservoir can be a hydrocarbon reservoir can be even groundwater, all sort of things we can characterize by computing seismic attributes, and one of the attributes we are showing about attenuation. With the passage of time, the seismic data have been acquired in huge amount, and we are thankful to the high performance computing system. Even if data volume is huge, even if the data lies in a very complex region, because of the high performance machine, that processing or imaging of the data, a huge volume of data, can be done with a reasonable time. But till date, whenever we produce the image, till date we interpret those images manually, and that interpreter struggle for manual interpretation, particularly when the volume of the data becomes very large and subsurface become very complex. So there lies a challenge. So acquisition, no issue; processing, no issue. But there lies a great challenge of interpretation of the seismic data to bring meaningful information of subsurface from the surface data. So how can we, is it possible to automate the process of interpretation? Is it possible to reduce the human intervention so that we can get quite accurate subsurface information with reasonable time and by reduction of human intervention? That's what our objective of this work. I am quickly presenting how we can achieve that. Nowadays, in almost all fields of medical, engineering, and sciences, we see that application of the artificial intelligence and machine learning is there, and that has been greatly used to automate the process. We have borrowed this same concept to the geoscience data so that we are able to automatize the process of interpretation. What we mean by process of interpretation? We mean the process of interpretation that we should be able to produce the subsurface image automatically. We'll be able to interpret some of the subsurface geologic features of its own by the machine itself. And this is the need of the hour, because with the passage of time, large volume of the data have been acquired, and we have also gone into the very complicated geological system. So their interpretation, if we want to do manually, we become tired, we do mistake, and becomes almost impossible. To alleviate this impossibility to get some sort of accurate image of the subsurface, we want to borrow the concept of the artificial intelligence and apply to the seismic data so that it automatically delineates some of the geologic features. I will show through the examples. And all of us know in the machine learning there are three important layers: that input layer, hidden layer, and the output layer. In the case of the seismic interpretation, we need to design a neural network such a way that the neural network can automatically pick up the subsurface feature from the surface data. Definitely, we need to do certain processing steps before applying to the artificial intelligence. What are the steps? I have listed over here in the left side: step 1, step 2, step 3, step 4, step 5, and step 6. Seismic data conditioning. And then we need to select some of the attribute. I mentioned in one slide that attribute is a characteristic property of a subsurface geologic feature. Then we need to train the system And for that, we have to identify example locations, and then we have to do some sort of testing or validation. Then we need to run the network to the entire volume of data. So in the seismic volume of data, we can identify a lot of attributes. Some of the attributes have been listed over here, and these attributes respond to different set of subsurface geologic features. That can be fault, that can be channel, that can be levee, that can be dike, that can be seals, that can be gas migration plumes, many things. And these attributes may be common. Some of the attributes will respond to some feature, and some one or two attributes will be responsible for only to a particular geologic feature. So we need to know, when we look into delimitation of the subsurface geologic features, we need to know what are the attributes that can characterize, that can define that particular geologic feature. So that is available in literature. There will be many attributes. Single attribute cannot do that, because I told that single attribute may respond to channel, single attribute may respond to levee also. But when we have multiple attributes, then we will be able to define that channel or levee system very clearly. Then this attribute information is linked to the output through the hidden layer. And that hidden layer concept, those who are well known into the neural system, they know how the input, how the hidden and how the output layer works. Just to make easy for the people, those who want to know how we can automatically define subsurface geologic body from the surface data, this slide is very, very important, and I will keep maybe 1 more minute to explain of this slide. Suppose we are given a set of seismic data, and within the seismic volume of data, there may be many geologic features. There can be fault, there can be mass transport deposit, there can be some sort of gas plume, all sort of things. Suppose our interest is to delimit the subsurface geologic feature on the mass transport deposit. So we look into entire seismic data. What are the seismic attributes that can define the mass transport deposit? We will not look into other seismic attributes. There may be 10, 15, 12 attributes which can define the mass transport deposit. So, few examples I am showing over here: low energy, variable dips, low similarity. Like that, there will be many sets of attributes which can define the mass transport deposit. So, using artificial intelligence, what we have done over here, we have amalgamated. First, we have extracted the attribute which can characterize the mass transport deposit, and that all those attributes we have amalgamated into a single attribute. That single attribute we have defined mass transport deposit tube meta attribute. And this is the basic philosophy of this automatic delimitation of the subsurface geologic features from the surface seismic data. So what we have done, since we have a huge volume of data, for training the system, we have taken 20% arbitrary data from the entire volume. And that 20% data have been taken randomly. And then physically, we see into each section where is mass transport deposit present, that we have defined by red. Where is mass transport deposit is absent, we define by blue. And this mass transport deposit presence and absence can be defined based on its characteristic property that we know. And we give the binary number. When mass transport deposit is present, we give 1. When it is absent, we give 0. So within the 20% data set, out of the entire 100%, we give the binary number 0 and 1. Now, using this artificial intelligence concept, we have identified many attributes of this input layer, and using the hidden layer, based on the feed-forward process, we generate the outcome, and that outcome lies between 0 and 1. So at this observation point, we know where is the mass transport deposit present, where is the mass transport deposit absent. Then, using the feed-forward process, we compute that value between 0 and 1, and then find the difference between the observed and prediction. And iterative way, the difference between the prediction and observation is minimized. And that minimization is adjusted, or minimization is done by adjusting learning rate, momentum, weights. Those who are familiar with the system, how we can minimize this difference between the prediction and observations iteratively by changing the different set of learning rate, momentum, and weights iteratively. Then when we get this type of fit and then a plateau, and parallelly, we also see that the machine has been learned properly. So out of 20% data, for the training we have used only 15% data, and the remaining for the training we have used 70% data, remaining 30% we have seen how the machine has predicted, and for that we see the validation that whether the machine is going to predict in the right direction or not. So once we are happy with the 70% and 30% of the total 20% volume of the data, and we find that this error curve has attained a plateau, that we see the machine has been trained. Now, and to check whether machine has been trained beyond the 20% data, one seismic section we have taken, and then we predict that what are the mass transport deposit. Then click on the seismic section, and we see wherever manually we predict the mass transport deposit, and whatever machine learning has predicted, that matches, and it shows the confidence the machine has been well trained. So now, once we find out the machine is well trained, then that entire system is run for the 100% volume of the data. And wherever the presence of the mass transport deposit is more than 0.7 threshold, we observe, because I have told that by doing the feed-forward process, we compute the binary value between 0 and 1. Wherever we find value more than 0.7, we know that there is a presence of the mass transport deposit. And this way, from the entire volume of the data, automatically, by looking into more than 0.7, we find out the delimitation of the subsurface geologic features, in this case, mass transport deposit. So this is, if somebody wants to know more, they can find out this Nature Scientific report recently published last year. Similarly, I am showing one more example from the Mari prospect. Similar way, we have identified a lot of seismic attributes, and that have been amalgamated from a chimney cube meta attribute, and by looking into the chimney cube meta attribute, we can understand how the gas plume into that basin has been migrating upward. Even on the sea floor, we can see the top marks of the presence of the gas migration or plume. So this way we can see how this has gone from Pakoara group to Kapuni group to Mahakatini group to Oeki basin into that region. So this way help us to know how the three-dimensional gas migration plume exists into that particular basin. Third example I am showing, again we have computed lot of seismic attributes which are responsible for the fault, and then we have amalgamated them into a single attribute called thin fault cube meta attribute, and we have been able to create a network of the fault from the entire 3D volume of data. And the prediction that has been shown by red color has been superimposed on the seismic section, what generally people do manually, and we see wherever there is a fault and the prediction, they match quite well. So this way, machine picks up the fault from the entire volume of the data and creates a mosaic of the fault system in the particular region. So this way it shows that artificial intelligence has been extensively used for automatic delimitation of the subsurface geologic features, and all these we have submitted into form of a book, and that has been accepted by WIHG, and very soon it will be coming out. And this will help us to give guidance to the professional working into the industry as well as researchers in different institutes to know the theory, definition, and large collections of the illustrations. So finally, in concluding remark, that artificial intelligence has helped us to make automatic interpretation of the subsurface geologic feature with reduced human intervention. And that has got wide applications, not only the delineation of the structure, but also delineation of the physical properties like porosity, permeability, saturations. We are extending this approach into Himalayan region for the assessment of the geohazards, landslides, earthquake, lithology, etc. Thanks a lot to my student. Thanks to DGH, ONGC for giving data, as well as CSR, MOES, MOP, NG for providing financial support. Thank you very much.